Okay, here we go again. Back for more division with square roots. We've got a couple examples left of that I'd like to try, and then I need to show you a little bit about how you can use square roots to actually solve an equation. So, a couple more simplifying square roots with division, though. If I was to give you something like square root of 11 over 12, once again, what should I do to break that down? I can't have square root of 12 in the denominator. The question is, do I want to take it times square root of 12 right now? Well, if you can break either of those numbers down to something simpler, you need to do that first. So I'm actually going to treat this once again like it's two separate parts. I'm going to notice that, hey, dude, 12 is really 4 times 3. And so I can actually turn the denominator into 2 times the square root of 3. Now, here's the important part. When you have something like this, the only thing you're worried about is you don't want square root of 3 on the bottom. 2 is happy as a clam down there in the denominator, and it wants to stay there. So when you go to get rid of the square root of 3, you only multiply by the square root of 3. Don't use the 2. It will actually make your numerator and denominator get too big, and then you'll have to reduce your fraction when you get done at the end. Only multiply by the square root. Don't multiply by the coefficient in front. Okay, consequently, when I do that, square root of 11 times square root of 3 is really square root of 33. On the bottom, I'm going to have 2 times the square root of 9. Well, what's the square root of 9? It's really 3, so I really have 2 times 3, or 6. So now I'm down to square root of 33 over 6. I should stop and ask myself, will square root of 33 reduce? Is there a perfect square number that goes into 33? And the answer is no. The only factors there are 3 and 11, so that one's not going to break down, and that's where we will leave our answer. Okay, now here comes the real fun and games. This particular process I'm about to teach you seems a little bit silly when you're trying to just simplify square roots, but this process we're about to learn here is useful in several other types of problems that we will run into later on this year. So it's a really important skill that you learn how to do it. Right here, doing it with square roots is one of those things I think is a little obsolete. But the general process of how this works is hugely helpful for many other problems. Okay, and what this deals with is, what do you do if you have more than one term? In this case, what if I have 3 plus 4 times the square root of 7 divided by 5 minus 2 times the square root of 7? Well, how do I get that to multiply so I get rid of the square root of 7 in the denominator? Okay, don't write this down if you're taking notes. Hopefully you're just watching the notes I printed for you, because I'm about to do this wrong, but I want you to see why it's wrong. If you just go, hey, I'm going to multiply by square root of 7, like we've been doing, watch what happens on the bottom when you do that. Because when I multiply by square root of 7, I have to take it times the entire denominator. It means I have to distribute it to both parts. That's going to give me 5 times the square root of 7 minus 2 times the square root of 49. Well, yep, square root of 49 becomes 7, and I get this simplified. But I now have a square root of 7 over there on the 5. I didn't get rid of it. So it does not work when you have more than one term in the denominator. It does not work to just multiply by that square root. So instead, we're going to undo this. And we're going to learn a new method. This is actually pretty amazing that this actually works. If you want to get rid of the square root and you have 2 terms, we are going to multiply by what's known as the conjugate. If this is 5 minus 2 square root of 7, when you multiply by the conjugate, and I'll spell that out for you, you multiply by the conjugate, you're multiplying by 5 plus 2 times the square root of 7. You change the sign only in the middle of the 2 terms. You don't change the sign on the front term, just the sign in the middle. And of course, though, if you multiply it times the denominator, you have to multiply that same expression times the numerator. And for those of you who have realized what this means and are out there moaning and groaning, yep, you get a FOIL. You get to do lots of FOILing. It's going to be jolly good fun here. So, if we want to do that, here's the amazing part. I'm going to do the denominator first because it's just absolutely fantastic what happens when you FOIL two conjugates together. Okay, so we're going to take first times each other, which means 5 times 5 is 25. Outers, I'm going to take 5 times 2 and get 10 times the square root of 7. Now, watch what happens. This is a miracle. When I go to do the inners, what am I going to get? Minus 10 times the square root of 7. And what's going to happen then? Yes, those two cancel each other out. That will always happen when you're working with conjugates. The outers and the inners will cancel each other. Now all I have to do is multiply the last. Well, 2 times 2 is negative 4. Square root of 7 times square root of 7 is really square root of 49. So in reality, I'm going to be left with just 25 minus 4 times the square root of 49, which I'm actually going to simplify here in a minute, but I also need to do it at the top. So right now I'm just going to rewrite that. We'll come back and simplify that farther in a second. You do need to multiply the tops together, and that requires FOILing. Now, those aren't conjugates. Those are totally different terms. Yep, you got to FOIL the whole thing. So 3 times 5 is 15. Outers, 3 times 2 is 6 with the square root of 7. Inners, 4 times 5 is 20 times the square root of 7. And then, of course, last, 4 times 2 is 8. Now, here's where I've been avoiding this, but it's time to talk shortcut. When you take square root of 7 times square root of 7, you're going to get 49. Square root of 49 is 7. Anytime you take a square root times itself, square root of 7 times square root of 7, you're simply going to get that number. It's going to be 7. So what I actually have there is 15 plus 6 square roots of 7 plus 20 square root of 7 plus 56, 8 times 7. On the bottom, I could have done the same thing. Square root of 49 is really 7. So in reality, all I have there is 25 minus 28. If you simplify that, you're going to get negative 3 in the denominator. On the top, if I combine like terms, 15 and 56 are going to make 71. 6 square root of 7 plus 20 square roots of 7 is going to give us 26 times the square root of 7. And you'd think, I'm done. But unfortunately, one other little detail. Mathematicians don't like negatives in the denominator of a fraction, particularly if you have multiple terms on the top. So the last thing you have to do is you have to move the negative to the top. Now remember, there's no difference when you're working in the land of fractions between negative 1 over 2 and 1 over negative 2. You can put a negative in a fraction wherever you like. You can put it on the top, you can put it on the bottom. So in this case, if we don't like it on the bottom, we choose to move it to the top, and we simply say, okay, you're going to change all your signs. You're going to make the bottom become positive. You're going to change all the signs on the top, which in this case makes them negative. So my final answer is really negative 71 minus 26 times the square root of 7 all over positive 3. And there you have it, your first one to multiply with conjugates. You can do, anytime you're doing conjugates, the denominator will always cancel those two middle terms up there, where the 10 square root of 7 and the negative 10 square root of 7 canceled. You only have to multiply the first and the last when you're doing the two that are conjugates of each other, because the middle terms will always cancel. So that's a bit of a shortcut for you. Now, like I said, having to do this for square roots is a little bit obsolete, but the idea of using conjugates and getting the middle terms to cancel, that's huge for us in several different places throughout mathematics. So we will use conjugates again in a better spot than using them for square roots. All right, last but not least, we need to do a little solving action here. And there's just a couple things I need to warn you about. You should remember this from Algebra 2, or from, excuse me, Algebra 1. If I ask you to solve an equation that contains an x squared, what do I get? Well, okay, how do I get x by itself? As usual, yes, I subtract 7. I end up with 3x squared equals 36. I don't want the 3, so yep, I'm going to divide by the 3, which is going to give me x squared equals 12. Now, here's the new question of the day. How do you get rid of x squared? You hopefully will remember then, of course, if I want to get rid of x squared, yes, I use our friends, the square roots, to get rid of x squared. The square root of x squared will give me x. You now have to break down square root of 12, which is 4 times 3, so you get 2 times the square root of 3. Now, here's the wrinkle. You only get, or I should say you also get something else. This is a difference, and I'm going to go back to a nice easy number to prove my point. If x squared equals 9, what are the actual numbers that x could equal in order for it, when you square it, to get 9? And yeah, you can get 3 or negative 3 here would actually make that true. When you are solving for x and you choose to put the square root on both sides in order to solve it, it means that you can get the positive or the negative answer. So if you square root both sides, you will have to put a plus or minus on every one of your answers. That's important. Okay. One other example of that. Suppose they give you a quantity squared equals, say, 25. Do the same thing. You want to get rid of the square, so we choose to square root both sides to get rid of it. I now have x plus 6 because the square root cancels out the square. And here I will get 5, but because I put the square roots on it, I will go, okay, it could be plus or minus 5. So now when you go to solve for x, you're going to subtract 6 to the right-hand side. You're going to have negative 6 plus or minus 5. It's actually going to give you two answers, negative 6 plus 5, which is negative 1, or negative 6 minus 5, which is negative 11. All right, last but not least, our teeniest bit of introduction. We're going to spend all of next class on this, but today I want you to see it slightly so that next class we're really ready to roll with this. We talked about there was such a thing as imaginary numbers, and here they come. We've always told you that you can't do the square root of a negative number because there's nothing times itself that makes a negative number. Well, mathematicians have need of being able to work with square roots of negative numbers. So in mathematics, when you can't do something, they say, okay, let's invent and do something new and prove a whole new theory to be true. And so in this case, mathematicians said, we're going to do the square root of negative 1, and we are going to name it I. And they call it, unfortunately, an imaginary number, which makes people think that it's not real or valid. Imaginary numbers have many uses in the real world that I'll go into next class. But yes, it's not a fake number, it's not something you're dreaming up. It's simply the square root of a negative number. If you are asked to do the square root of negative 16, you simply think of it as 16 times negative 1. Square root of 16 is 4, square root of negative 1 is I, and so you have 4i. So, quick like, what's the square root of negative 121? And yes, whoever's out there hollering 11i, you're right. You simply pull the negative out as an I, break down the roots exactly the same as you have before. If they ask you for square root of negative 40, you think of that as 4 times 10 times negative 1. The 4 comes out and it's a 2. The negative 1 comes out and it's an I, and you're left with a square root of 10. You treat it exactly the same as any other square root. You just pull the negative 1 out and make it an I. We're going to stop right there.